Welcome everyone. I'm really happy to be here and to be able to present a talk to you all here at Troopers. My talk's named Cat and Mouse or Chess, and you will find out in the meanwhile of the talk itself why I named it like this. First of all, the agenda. What am I talking about, or what's the structure for the whole talk? In the very first place, I'm going to talk something about myself. So who am I? What am I doing currently? Then I'm going to give a slight overview on how endpoint detection and response systems work under the hood and how they detect known malicious payloads. Afterwards, I'm going through, or I'm summarizing in the recent years published known techniques to bypass Userland Hook-based detections from EDRs. And afterwards, I'm going to give you an introduction on my own idea for a new approach to also bypass Userland hooking techniques, detection techniques. And I'm going to show you what challenges I personally faced by implementing this idea and the proof of concept. And afterwards, I'm going to actually show the proof of concept and to show you what it's about and what is happening under the hood with a demo. So first things first, who am I? I'm team leader at the pentest/red team from ITsecurity, which is a company based in Germany. And what I like to do the most in my work time is breaking into company environments and escalating privileges there. Obviously, not only to do it like Infractor does to do some malicious stuff, but in the very end, we're simulating an attacker, and afterwards, we're giving the customers hands-on recommendations on how to get better security afterwards. Inspired by the community, I think many things that all pen testers or red teamers are doing relies on open source stuff. And inspired by the community and by everyone else who publishes stuff, I personally also like to share my knowledge. And for this reason, I have a personal blog post page. I published some videos on Twitch, which landed on YouTube afterwards. I published a lot of scripts and tools on GitHub. So this is what I'm doing mostly in my spare time, by the way. Also I have special interest in AV or EDR evasion-related topics. Mainly the thing is, if I'm in some environment, I would never ask the customer to disable that because it's a challenge. In the very end, if you're in an environment and if they have something in place which should block you, I always saw this as a challenge, and I never accepted this is not working. So I'm always in, okay, how to evade that, how to still get my payload to work, and so on. So this was always of special interest for me personally. So how do endpoint detection and response systems, or short EDR systems, actually detect malicious payloads? What are they doing under the hood? On the one hand side, there is Userland-based detections. So Userland means it's all processes that run in the context of a user and not of the operating system itself. And EDRs can do, for example, in static analysis, so they can check the file, they can do a signature scan, they can check the properties, they can check for certificates, they can check the metadata, and so on. But they are also doing one thing, and this is, from my point of view, the thing that what they mainly use to detect malicious payload. This is Userland hooking. And I'm going to explain Userland hooking in the following slides because this talk is mainly about how to bypass these. So I'm going to talk about that later on how that works in depth. Then they can also use stack trace analysis. On the right-hand side, you can see a screenshot from an example stack trace. And from the kernel end, they can also detect stuff. So in the very end, they have a driver. They register with that driver on the Windows operating system, and they can, for that reason, also do an analysis from the kernel end. So from the, where only typically the operating system itself does stuff. And they have the options of using kernel callbacks here to detect malicious activity, or they could use ETWTI, threat intelligence, which is a provider by Microsoft, where they can subscribe and get specific events. But I'm not focusing on these kernel-land-based detections and bypass techniques here, but only on the Userland, because from my personal experience and from what I faced in the past, I think this is, as I said, the main thing what EDRs use, and the kernel-land-based detections are yeah, not that much used as userland hooking. So what is userland hooking, or what are userland hooks? In the very end, the EDR vendors typically have their own DLL, so a dynamic linked library, which they load from the kernel directly into any userland process. So if you, for example, spawn a PowerShell, then in this PowerShell process, the EDR's own DLL will be registered and loaded. And what do they do when they loaded their own code, their own DLL? In the very end, they place, and this is the name, userland hooks for specific Windows APIs and patch the memory for these Windows APIs. So, for example, in this screenshot here, you can see that there is the function ZW protect virtual memory or NT protect virtual memory. And a typical function or a typical NTDLL function would look like this one above here. So it looked like morph R10 to RCX, morph EAX 4F, and afterwards the syscall instruction is called at some point. And if the EDR vendors place their userland hooks, or if they place their own code, instead of, and if my malware would actually call specific Windows API functions, then instead of the function getting called, there is a jump instruction. And the jump instruction, in the very end, means if this function is called, if some malware wants to call this, then instead of actually executing what the malicious software wants to execute, jump to the memory region of the EDR DLL. So there is a jump which goes to the EDR DLL, and the EDR DLL will then afterwards analyze the input arguments for this specific Windows API. So it can, for example, say, okay, the NT protect virtual memory or ZW protect virtual memory is getting called, and what is happening? What protection values should, for example, be changed here? And by doing that, they can then detect malicious payloads on runtime. So it's not about detecting a malicious file, it's not about a signature, nothing like that, but instead it's like a little bit like a behavior-based analysis, because they can on runtime see what the malware does and can check what it wants to do, and they can live prevent it. So if they think or found something malicious, they can also, for example, kill the process. Yeah, I'm going to give one more example here, because I think if you never heard of userland hooks, or if you never faced that yourself or did a deeper analysis, then it's hard to understand this concept in the very first place. So I'm going to give one more example here. So this is an example on how a malware could actually execute malicious code in a remote process, for example. If I, as malware, want to execute code in a remote process, I could use these Windows 32 APIs. In the first place, I could open a handle for the remote process with the Windows API function open process. Then I could use virtual alloc x to actually allocate some memory in that remote process. Afterwards, I can use write process memory to write my malicious software or my malicious code into that remote process. And afterwards, I can call create remote thread to actually execute this malicious malware, which I put into the remote process. And create remote thread, in the very, very end, calls nt create thread x, which is a function from ntdll. And typically, userland hooks are also placed in ntdll memory, because this is the very last or these are the last functions that are called before everything goes into kernel land. So this is the last thing that always has to be called. Yeah, and if we take a look on the definition for nt create thread x, for example, so this is just on how could this function be called, we can see that there are different input parameters, and one input parameter is the start address parameter. And the start address in the very end means so we are creating a new thread, and the start address contains the code that has to be executed in that new thread. And the EDR, if it has a hook placed on nt create thread x, can live check what is happening and what is the start address, what has to be executed. And it can then do, for example, a memory scan for that specific location. And with a Yara rule, for example, it could check this specific memory region from the thread who has to be created. And if it finds some known malicious code, like, for example, a Cobalt Strike beacon, Sliver beacon, Covenant shell code, or whatever, then it can say on runtime, okay, this function is not called at all, but instead I found malicious code, I will kill this process now. And this is what they are doing in the very end. Yeah, I think this may have gotten a bit better understandable if you didn't fully understood it before. Yeah, kernel callbacks is in the very end, I would say, or I would compare it in terms of it's a little bit like Userland hooks, but they are not really patching memory or something, but they can, for specific events, like the events that you see on the right-hand side screenshot, and this is also thread creation, memory allocation, it's about a new process is created and stuff like this. They can, when this event occurs, they can intercept anything from kernel, so from the OS operating system region, and they can then also prevent or interact or do something. And this is something which we, as attackers, cannot really bypass, at least not from Userland. Or, yeah, okay, it's possible. I'm working on some stuff for that, but yeah, it's not the topic for today. Okay, then there is event tracing for Windows threat intelligence. As I already said, this is like event-based subscriptions, so the vendors can subscribe there, they can receive events. These events are, for example, here in the second screenshot. It's also about allocating memory, it's about protecting memory, it's about creating a new thread, queuing an APC, or whatever. And they can then, in this case, interact after they got this event. It's not really live, like kernel callbacks, but it's they receive the event and then they can do some stuff in the process. For example, they could check this thread stack trace to see if there's some malicious code, something in a memory region which is not based with a DLL on disk and stuff like this. Or they could also do, for example, a memory scan afterwards. Yeah, but this, as I said, is, from my point of view, from my experience, not used as much as Userland hooks, and for this reason I'm focusing on Userland hooks here. Yeah, but how could attackers, or how could a malicious software actually bypass these Userland hooks? There were many different approaches published in the last years, and they were public for many more years, even in the gaming industry, for example, on how to bypass these things. There is, for example, unhooking. I'm going to explain that shortly. Then the usage of direct syscalls. Then you could use, for example, hardware breakpoints to bypass Userland hooks. You could use DLL entry point patching. Yeah, and then I'm going to have just one slide per technique to give you a slight overview on what these like older techniques or the published techniques are about, and afterwards I'm going to describe the new idea and approach. So unhooking first. As I said, the memory is patched by the EDR, so the EDR places its own code into the memory. But if we as attackers just take like the code from NTDLL from disk, which is not patched because they typically don't manipulate NTDLL on disk, then we can grab the code which has no hooks, and we can again override the hooks in memory, which are typically placed in the text section. And if we do that, if we grab a fresh copy of NTDLL from disk and use this content and override the memory of our own process with that fresh copy, then we actually remove the hooks, and on runtime the EDR cannot analyze anything anymore because there is no jump to the DLL. It does not take place anymore. This is one technique. Another technique is to actually not call the Windows APIs the typical way, let's say like this, but instead we're using NTDLL functions directly. This means we could, for example, embed the NTDLL functions, which we want to call as ASM stubs, directly in our code, and we could say execute this ASM code or assembler code on runtime, and then it's then also not hooked because we have full control about what is going to execute it. And by just embedding the NTDLL functions in our code itself, we are also avoiding hooks because we are never calling NTDLL memory directly. We could retrieve these syscalls or NTDLL functions, stubs, for example, from memory. There's existing techniques like healthgate, recycled gate, and many other star gate techniques. They were somehow named like this. But what they all do is they retrieve the content not from a fresh disk, not from a copy from disk, but instead they receive the code that has to be executed from memory, so from NTDLL memory. Because syscalls always look the same, and if one function is hooked, then they can, for example, say, okay, I'm going to check the next function, which is not hooked, I'm going to grab the content from there, and yeah. Third way to use direct syscalls, or third technique, is partially or fully embedding the NTDLL functions in your own code. There has been proof of concept codes like, for example, this Whispers version 2 or this Whispers version 3. There is even more, but I think these are the mainly used ones, or the ones at least that are most used by pentesters, red teamers in the community in the moment. Yeah. Okay, hardware breakpoints. What is that about? In the very end, hardware breakpoints can be used to do some debugging stuff in a process, for example. So you can place hardware breakpoints to specific memory regions, and if that specific memory region is hit on execution, so for example, if ZW protect virtual memory has to be executed, and we have a hardware breakpoint there, we can intercept what is happening, and we can do our own things, or we can execute our own code then there. And the technique which was published here is, I think the first one which was published is tempering syscalls, the proof of concept on GitHub. And what that is doing is, it's setting a hardware breakpoint on the NTDL functions which are getting called, and then it's hiding the input arguments in that moment. So even before the jump to the EDR-DLL takes place, we can, with our own code and with the hardware breakpoint, remove the input arguments from stack. We just replace them with, for example, 0, so that they all look that their input was 0 instead of. Let's go back to the thread creation, for example. There would be a start address, and we replace that with 0. So if the EDR checks the start address, then it will just see 0, and this is not malicious. It cannot do memory scan for 0, and it will just continue and say, okay, this is fine. And we're backing them up somewhere else in memory, and then the proof of concept is single-stepping to the actual syscall instruction. And when the syscall instruction is called, or before that is called, this proof of concept is restoring the old input arguments again, because if we don't do that, then we would break execution flow. It would not work anymore. So it's restoring the input arguments, then the syscall instruction itself is called. And by doing that, the EDR just does not see what really gets executed in the very end. It just sees our fake input arguments. So this is what this technique is about. Yeah. Then there is DLL entry point patching, which is something very different from all the other techniques that were published before, because the proof of concept was from Thierry Coburn, and the tool is named SharpBlock. There's also a blog post which is linked here in the slide. So this proof of concept is creating a new process, and it's creating that new process with the debug only this process flag. And this setting this flag when creating a new process in the very end leads to the fact that we can then act as a debugger for this newly created process. We can debug it. We can intercept live events, and we can do some stuff before these events even are executed. And there's, for example, one event, namely load DLL debug event, and we can, for example, check for these events. And if we see, okay, some DLL wants to be loaded or is already loaded, was just loaded, then this specific event occurs, and we can intercept. We can do some stuff even before the DLL itself can do some stuff, because we are a debugger for the child process. And the idea for this proof of concept was to patch the DLL entry point so that it looks like this. In the very end, they are placing an 0xC3 instruction into the entry point, so that the memory of the EDR DLL then looks like this. And if the EDR DLL wants to place its hooks, or if it wants to execute some stuff, for example, to place the hooks, then instead of doing that, it would just return true and exit, and then the DLL is not in the process anymore. So this it does not prevent the DLL from loading, but instead the DLL is patched in memory, then it's returning true, just exiting, and it's not in the process. There are now Userland hooks, and for this reason you have a new process with no EDR DLL anymore, which can do analysis. Yeah, these are the existing techniques, or a summarization of the existing techniques, at least that I know about. And then at some point, I had the idea for a new approach. In the very end, I was inspired by reading a specific blog post, namely a blog post by Alejandro Pina, who was describing the process of, or it is a new AMSI bypass technique in the very end. And this proof of concept is hooking functions, namely NT-create section, for example, from the DLL loading process. And by hooking these functions from the DLL loading process, so we are placing hooks ourselves as malware, the same thing that the EDR vendors do, but we are doing that for ourselves to intercept some stuff. And if we place a hook for these DLLs, that we can then manipulate the flow of loading the DLL. So, for example, this proof of concept was about bypassing AMSI DLL by not loading it. So if you have a new process, AMSI DLL is typically not loaded, then it's placing a hook for NT-create section. And afterwards, it's like loading a C# binary, for example, because loading a C# binary would trigger AMSI DLL to be loaded. And when AMSI DLL is going to be loaded, or when it should be loaded, then our hook would just say, okay, I have to create a section here with NT-create section for this DLL to get it into memory, but we just return fail, or our hook replaces fail, so that the process thinks, okay, I was not able to create a new section, so I cannot map this DLL into memory, and then it will not be loaded into memory. So effectively, this is a way on how you can prevent a DLL from loading into your process if it was not loaded before. So this can only be done for DLLs that are not already loaded in the process. And this is the mainly relevant thing, what we will see if we want to use this approach for EDR vendors or for EDR DLLs. Because AMSI is not loaded typically in a process. It's only loaded if you load some script which has to be analyzed by AMSI. But in a new process, typically for EDR DLLs, this cannot be done because EDR vendors or the EDR software is typically like the white player in a chess game, because they can do the very first moves like the white player does by placing the hooks directly after loading the DLL from kernel. And the thing is, they have a kernel callback to see, okay, a new process was created. Then they can say, when the new process is created, our DLL should be loaded first. It's not the first. The first function is always NTDLL. The first library is always NTDLL, which is loaded. But then afterwards, if they do it properly, their own EDR DLL gets loaded directly after NTDLL. So for basically any existing userland process, the EDR DLL is always loaded. And if it's always loaded, we cannot patch the functions which are used to load a DLL and to prevent it from loading, because they are already loaded. So this proof of concept is not applicable to bypassing EDR or stopping EDR DLLs from being loaded. Yeah, so I already said that. Yeah, the idea for the new approach, but this was still in my head. And I had the idea, okay, but there is some specific cases in which the EDR DLL is not loaded. Namely, if we create a suspended process, which is just with a specific flag, namely the flag create suspended, then the newly created process will not have the DLL loaded, not the EDR DLL, because the suspended process always only has NTDLL loaded and nothing else. And this is a cool fact that we can use, because if we create a suspended process, then we can also place hooks for NTDLL. NTDLL is already loaded. And this is where my whole idea for a new approach started. So this is like the structure on how things work, or how this idea works. We have our malware, and this malware is creating a new suspended process. This suspended process has only NTDLL loaded. And we can then allocate memory in that newly spawned suspended process and inject custom self-written shellcode into that remote process. And afterwards, we can remotely hook these specific functions which are used to load a DLL, for example, NT-create section. It would also be possible to use alternatives, but that is described in the Alejandro Pilar blog post as well, so you can take a look at that if you want to know more about it. And if we place a hook for this function that jumps to our shellcode, which we placed there before, and resume the process afterwards, then we are, in the very end, our code is already there, and our code is there even before the EDR DLL is there. And this is the idea, because we can then intercept the loading of the EDR DLL by saying, okay, anti-create section failed, for example, and saying, okay, this just didn't work, and then the EDR DLL will not get loaded at all because our code was there first. We have full control. Yeah, this is the idea, or this is the idea which I had in my head, and it took many months for me to really implement this. This was in my head only for many months. At some point, I started implementing that, but when doing that, I faced several challenges and or problems. And I would like to give you an overview about these, because it was not as simple as I first thought that it is. So the first thing that I faced is, which I had to do here in this case, is writing position-independent code myself. I never did that before this project. I was using or was doing many other stuff, but I never wrote shellcode on my own. And if you're doing that, then you typically have to write everything in a like style, or you have to write it that all the code that is all the code that you have is placed in the text section afterwards. Because the text section is like the dynamic part of the binary. If we have, for example, a string, we cannot just use a string in position-independent code, but we have to split it up, and then it's concatenated again on runtime, because if we do it like this, then it's in the text section. We cannot use, for example, global variables, because global variables are not stored in the text section, and they are just not known anymore. So we have to find some other stuff or other alternatives to exchange information between different functions instead of using global variables. We have to resolve all APIs on runtime, because we cannot do it the typical way, like just importing the DLL and loading the specific APIs, but we have to resolve them on runtime. We have to pass the PEB, we have to look for where is this specific DLL, then we have to pass for where is this specific function, then we have to cast a function pointer to that function, and afterwards we can call it. So it's it's not super complicated. There are proof of concept already. There is code which is position independent, or different code, and you can take a look at these. We also have to replace the main CRT startup routine with our entry point. So if we have some function which has to be executed, like for example a main function, we have to place a jump in the very first place of or at the start of our executable to that entry point, because otherwise the main CRT startup routine would be called, and this would somehow disrupt or our input parameters and stuff from memory. It would do some stack stuff. This is not a good thing. So we have to replace the entry point in the very end. Then this is specific for my proof of concept only. This is not for writing position-independent code, but this is specific for my proof of concept. It can only, so the shell code, the position-independent code, can only use NTDLL functions, because only NTDLL is loaded. And the process initialization is not even finished yet, so we cannot also say, okay, now load kernel 32DLL or whatever, and this is not possible. I tried that, and the process just crashes. So we can only use NTDLL functions there, and so the proof of concept in the very end only uses NTDLL functions. I also had to replace many, or write many functions on my own, or rewrite them manually. Or GitHub Copilot did that for me, and I just wrote a comment. Please write a manual implementation of string compare, for example, and this was pretty good, the result. So I made it easy in this case with some functions. Others were more complicated. But for any of these which I mentioned here, I had to write like a manual function instead of using the built-in functions, because they cannot be used in position-independent code. I also wrote a logging function in my code, because if you're writing position-independent code, debugging is a real pain, because you cannot use, especially if you have only NTDLL functions, because you cannot use functions like output debug string A to output something into a debugger to see what is happening, but because this is not a NTDLL function. So in the very end, I was writing a logger function with NTDLL functions only, which creates a text file, places the debug statements, whatever I want to know what is happening in the moment, I place that in that specific text file, and yeah, then I can also troubleshoot stuff. Okay, then there were more challenges in the implementation. For example, one problem is you have to, at some point, get back the original content of NT_create_section. Because if we placed our hook to NT_create_section and the code is resumed, then our code gets executed, our shell code. But if it's some legitimate DLL which has to be loaded, like not the EDR DLL, but kernel 32 DLL or something else, then we have to call the original NT_create_section function again. But this is already overwritten. This is overwritten by our hosting process. And one idea that I had in this case is we can use an egg hunter here, for example. This is what you see on the bottom. So it's just one little byte stub with dead beef, dead beef, dead beef. And our host process can look for these this specific byte array in the shellcode, and the host process also knows about the original value of NT_create_section because it can just copy that over into a byte array before placing the hook. So we get back the old or the original value of NT_create_section from the host process. Then we are overwriting the egg in our shellcode with the original value, and then our shellcode can, on runtime, again restore NT_create_section because the value is stored in our byte array, and it can call it. So this was one solution. There would also be, it's also possible to rewrite the code in terms of you could, for example, implement Hellsgate or Tartarusgate or whatever, because in the very end, NT_create_section is a syscall, and to get the original content of this syscall, you could also use other techniques. This is just one, and it was, in this case, the easiest for me. I didn't want to implement Tartarusgate in this proof of concept. Yeah, then one more thing. If you take a look at existing position-independent code, which is on GitHub, like for example handle cuts or Lastenzug or stuff from Chetan Nayak, who wrote many stuff in position independent, then they all have this align stack part, these ASM stubs here in their code. And this is more or less, they properly align the stack for 16 bytes, I think. And if you're not doing that, then your code may not work properly, your shell code. But this is not a thing that we can do in our proof of concept, because if we do that, then this assembler code is doing some stack modifications. And these stack modifications make or corrupt the input parameters for NT_create_section because they are on the stack. So this cannot be used. What are we doing instead? Instead, we are directly jumping to the function which is the hook of NT_create_section, which blocks DLLs from loading. And we don't have to do the stack alignment in our proof of concept because the function that typically calls NT_create_section already aligns the stack for us. So we don't need to do that at all. This is a special case. We can just directly jump, then all input parameters are not corrupted, and the stack is already aligned, and this is fine. So this is also a special case for this proof of concept. Then there is one more thing. Yeah, it was not as easy as I said. One issue after another. You have at some point to decide or to choose which error code to return to for NT_create_section. Because if you do return an error, like for example this 4.5 value in the very end, this NT status code, then you will get this error message, which just says, okay, the DLL failed to load. It was not possible to load this specific DLL. In this example, it's for an McAfee DLL. For those who are English, sorry that it's German, but it was easier in this moment for me to make the screenshot in German. So this will appear, and this will stop execution, because you have to press OK, and after pressing OK, the process is resuming, and in some cases, returning an error blocks the EDR DLL, and in some cases, you have to return 0 instead, so that the EDR DLL thinks the DLL was properly mapped into memory, and somehow it will not get loaded then, because in the very end, the section was not created. So it's about fiddling around with the error code. This is just a hint, more or less. If you want to modify the proof of concept code, if you want to block EDR DLLs, you have to fiddle around with the error code. For some EDRs, it's about returning an error. For some, it's returning 0. And in some cases, you get this error, in some not. It's about how the EDR handles the status codes for NT-create section in the very end. Okay, I already said this. Yeah, but in the very end, what I faced or what I saw is using a return status code of 0 was, in my testings at least, better to block EDR DLLs instead of returning an error. But my proof of concept is returning exactly this error code, because this is only specific for PowerShell and AMSI DLL, because my proof of concept is blocking AMSI DLL or preventing AMSI DLL from getting loaded in a new PowerShell process. And in this case, this error code was better. It does not even show up an error message. But if you return 0 for PowerShell and AMSI DLL, then the process will crash. Because the Windows operating systems expect, okay, the section was created properly, and then it will crash because it will continue with execution. So some cases, you just have a crashing process. So this is what the return value problem is about. Yeah, the proof of concept itself, I named that Ruy Lopez. Ruy Lopez is a chess technique, or like a starting technique for the white player, because what I said before is the EDR vendor typically acts like the white player in a chess game. But if we get our own code into the remote process, it is executed even before the EDR DLL can start its stuff. And this way, we somehow get the white player ourselves for that newly spawned remote process, and we can do the first steps. So the idea was to name it like this. And yeah, as I said, the proof of concept will create a new PowerShell process, and then it will prevent AMSI DLL from being loaded. And I'm going to show that now. Or not, because my VM is not running anymore. So you have to wait for, I don't know, 5 minutes maybe? Or maybe 2. Oh no, it's just, okay. Let's do this in full mode. So as we can see here, in this case it's Defender. Real-time protection is on, cloud protection is on, and we have our proof of concept here. It's an executable, and if I run that, it will first spawn a new process. It will then get the address of NT-create section. It will inject shellcode into that remote process. Afterwards, it will allocate memory. It will push the shellcode into the remote process. It will place the hook for NT-create section to actually that it also that it does a jump to NT-create section. And yeah, we first have to also look for the egg in the shellcode. We have to replace this egg to get the original value of NT-create section back. And afterwards, we are resuming the process. And when the process is resumed, so all these sleep times in between are just for the demo effect. You can also make this way faster by just replacing sleeps. It was just to show you guys, or to explain it when it's executed. Okay, sometimes, I cannot tell you why, not fully, I have to still do some troubleshooting. Sometimes, specifically for PowerShell and AMSI DLL, it works only for the first time, and it crashes for the first time, and it works in the second time. Don't ask me why, so there are some edge cases, but still, if you are in a pen test, for example, this technique is still nice because you can just spawn PowerShell, even with a second try, and afterwards load everything you want, because nothing is preventing you anymore. AMSI is the only thing that defeats you, or that is your that can block you for loading PowerShell scripts or something like that. And yeah, if we prevent AMSI DLL from loading, then we are good to go. So let's check. Typically, if you execute a new PowerShell process, and if you like do, for example, or if you just say AMSI scan buffer, this is a string that is typically blocked by AMSI, as we can see here. I spawned a new PowerShell process, and I set AMSI scan buffer as input, and it just told me this script is malicious, and the content has been blocked by your antivirus vendor. In this case, this did not happen. So in this case, AMSI scan buffer was just not recognized as a known command because AMSI is not loaded at all. And we can verify that by checking its DLLs with Process Hacker, for example. Let's do that. I hope this is the correct process because, yeah, this is not the correct process. This is the one which has AMSI loaded. So this is how it looks like in the normal way. And this is how it looks like, or how you should have experienced it in any PowerShell process, because normally you cannot prevent AMSI from being loaded. But in this specific PowerShell process, if we filter by name, you can see there is no AMSI DLL. It's not loaded. It was prevented, and it's not loaded at all. And for this reason, the proof of concept worked, and it's verified that this worked. What could someone do afterwards, after preventing AMSI DLL from being loaded? We could, for example, load some malicious script. Hopefully, I still have internet access. I tested this some minutes ago. We will see. For example, we could load WinPorn, which is a script which I wrote over the last years. And it was not blocked. It was not prevented. It is loaded now. We can afterwards execute the main function to run the script. And it works. It's not blocked. It's not prevented. And afterwards, we could, for example, say, OK, now that we loaded WinPorn, we're going to load Mimikatz, for example, just because we can. And Mimikatz is loaded. We can execute Mimikatz here. In this, but no. Good news on the one hand side, bad news on the other hand side. Now the memory scanner by Defender is triggered because AMSI DLL is loading some specific DLLs in a specific order, and this event of loading these specific DLLs triggers a memory scanner, and the memory scanner finds Mimikatz in memory. We can still prevent this for Defender by just providing input arguments, and then the memory scanner is not as fast as Mimikatz with execution and with exiting. So that way we could still execute Mimikatz by providing the input argument first. But you saw it was in memory and it was loaded. But then another protection mechanism blocked it or killed the process in this specific case. Yeah, OK, I could not even execute coffee here now and answer. But this worked 5 minutes ago. And 5 minutes ago also the memory scan did not trigger. Don't ask me why. Sometimes Defender is just strange and it's not easy to explain what is happening and what is not. So sometimes it's blocking stuff and sometimes it's not. Yeah, fiddle around with that on your own. Feel free to try that stuff on your own. In the very end, the important thing is that AMSI DLL is getting prevented from loading, and you can more or less load any PowerShell script and execute PowerShell scripts. If you do that with Mimikatz, you may trigger a memory scan, which is another protection mechanism. It's also possible to bypass that, but different topic, maybe a different talk, I don't know, we will see. Yeah, OK. I tested this technique against multiple EDR vendors and put the DLLs for these specific EDR vendors into the code. And when testing this, it was not published at all. I had neither an alert from any vendor, and it was also not prevented from any vendor. So in any case, the DLLs were blocked, and I could execute whatever code afterwards without being detected by Userland Hooks. This did not work for all DLLs, however, to be honest, because some DLLs, for example, SciInject DLL from one specific vendor, is, as the name suggests, injected into the process, and it's not loaded the normal way. And if the EDR vendor injects a DLL, this proof of concept cannot block it, because it just doesn't work. I'm not going to explain that in depth here now, but it's very, very few DLLs that are injected instead of getting loaded the normal way. And there are also some edge cases for DLLs if the EDR vendor is not properly handling the anti-create section return value, then it might lead to a crash for some DLLs. So if you prevent some DLLs from loading, for example, this EDR.NET DLL, then the process will crash. In this case, EDR.NET DLL is not responsible for placing hooks, so it should not. You don't need to block it from loading. But also here, you have to fiddle around with which DLLs can be blocked and which cannot. And in some cases, you might face a process crash because the EDR vendor is not properly handling the status code of anti-create section, and it's still continuing with execution, and then something breaks. This technique cannot be used against Defender for Endpoint, because Defender for Endpoint is not loading any DLLs on its own. It's not placing Userland hooks. It's not using Userland hooks at all. It's mainly using ETWTI for everything. And for this reason, this technique is not possible there. Just if someone wanted to know that, or if someone wanted to test it against MDE, there is no DLL. You cannot block a DLL from loading. Yeah, is that technique OPSEC safe in the very end? This is something you might be interested in. In the very end, we have to say injection and hooking are techniques that are that have well-documented IOCs on the one hand side, private committed memory, for example. Finding a hooked function is also easy if you analyze the memory of a process. And blue teams, or especially hunters, could easily find those IOCs and find out that this technique was used, because they are well documented and you will just find about this stuff. But the good news is, an automated detection for this technique and for these injection hooking stuff and so on did not apply, at least not when I tested it so far. Because EDR vendors are not checking for these IOCs. They are not checking if a new DLL was spawned or if it was resumed, first spawned in suspended mode and then resumed. They are not checking NT-DLL for hooks. And because they are not yet, maybe they will do in the future, checking for hooks, this technique works and is not detected, at least in the moment. Yeah, OPSEC improvements. It would be an improvement, or it is an improvement, to use also Userland hook evasion techniques, so the existing ones, for the host process. And this is what I didn't want. I published the code already a month ago when I was at ZeefCon, but I didn't want to have no modifications at all when being at Troopers. So you can already make a check mark on this one, because I will release a new version after this talk, which is already using direct syscalls to inject the shellcode, and which is also using direct syscalls to place the hook. So this is already done by me, and I will publish it after this talk. Then you could, for example, modify the shellcode to so that it can also be used in an RX region, read execute instead of RWX. But this needs some modifications. I put comments into the code so that you know what to change, what to modify to get the state. You could use, for example, RP hashing instead of plain DLL names, because in this case, AMSI-DLL is prevented. If you take a look at the shellcode, you will see the string AMSI-DLL somewhere in it. If you block EDR DLLs, you will see this string. But if you use RP hashing instead, for example, or hashes of these names, then these will not appear somewhere in the shellcode, and they cannot hunt for it, they cannot build signatures for it. And what you could do to avoid this whole IOCs for hooks is the usage of hardware breakpoints, for example. You could spawn the new process in a debug state and place hardware breakpoints there instead of placing a hook. And by doing that, you could also like do a jump to the shellcode when anti-create section is called, and this will not have any IOCs for hooking. Okay. Is this good for initial access payloads? This is one thing which I added, which was not in the slides 1 month ago, but some people told me like, okay, this technique cannot really be used for initial access payloads because it's spawning a new process, it's hooking, it's doing injection and stuff, but in the very end, it can be used for initial access payloads. For example, you could do something like this here. You could check the current parameters for your process, and if the parameters are 0, so if no input parameters are passed, then we are going to spawn our own process, so our own executable, again, and we are passing some parameters, and we are spawning our own executable in suspended mode. We are injecting there, we are placing the hooks there, and afterwards resuming that. And because we placed some input arguments, this first check will fail for the newly spawned executable, and instead it will execute malicious code. So this would be one approach to also, with one executable, execute itself again and get rid of EDR hooks in that newly spawned process. Or you could just embed code, your malicious code, your executable in an array. You could write that executable to disk somewhere and just start that newly dropped malware and also go for the Rule-Lopez technique, and then the new process will not have EDR DLLs loaded. Okay. The repository is already placed in this URL, so if you want to take a look at the code, if you want to modify, fiddle around, whatever, feel free to go on that URL, and I will update the code, as I said, in a few minutes in terms of that it's using syscalls for shellcode injection and for placing the hooks after this talk. Okay. One more thing, alternative usage ideas. You could, for example, also block WLDP to bypass device guard or trust checks. This could also lead to unexpected behaviors. I did that for PowerShell as proof of concept, and some stuff was weird afterwards, but yeah, you can, still it's working. You could also block custom AMSI provider DLLs, so all the EDR vendors, or many of them, are using their own AMSI provider DLLs. You can block them. You can also bypass AMSI for EDR vendors this way. You could also modify the proof of concept shellcode, threadless inject style. Threadless inject is the proof of concept published by CCOP as well, which is not using or not creating a new thread for shellcode execution, but instead it's when a legitimate function is called, then the shellcode is called instead. So it's more or less, yeah, it's also like hooking. You hook some function, and when this is called, then it will jump to your shellcode, and your shellcode gets executed instead of creating a thread. And as NT-create section is always called, and it's even called before process initialization, we could also block EDR DLLs, and afterwards we could execute our shellcode, which is also embedded in the shellcode, or we could decrypt it on runtime and execute it to have shellcode execution in the newly spawned process. And this will not be done with a new thread, because we don't need a new thread to do that. So we can avoid some further IOCs here. Okay. I have to give some credits, because some people helped me all this way. Sherry Colburn helped me with many things. I had questions overall here and there, and he even made a short phone call with me to solve some of these questions, or to troubleshoot that. So big credit to him. Sven Rath gets credits because I had this idea in my head for like 5 or 6 months, but he was the person hitting me up and saying, okay, we can write code. I can start with that, and we can do that. I asked him, do you think this is an idea which is applicable? And he said, yes, it sounds good. It sounds like this is possible at all. And then I was like, okay, then I'm going to also start with that. And yeah, so he initially like motivated me to start with this proof of concept. Then Alejandro Pina, because he was writing the initial blog post for the AMSI bypass technique, which I'm relying on. And Charles Hamilton, as well as Chitan Nayak, helped me when I was writing position-independent code, because these are 2 persons who did that in the past, and I just hit them up with, here, I have this and this problem, and they were like, okay, you could do this, you could do that, whatever. So they also helped me. Yeah, and GitHub Copilot was my copilot when coding position-independent code, and I was also answering many questions to ChatGPT, which sometimes lead to very incorrect results, but also sometimes it lead to good results and to helpful answers. So this is also credit for AIs. Okay, any questions?